In this lecture, we'll do two more examples of working with geometric series. Here we have sum n equals 0 to infinity, 1 plus 2 to the n over 3 to the n. The first thing I'm going to notice is that I can break this up into two separate sums, so sum n equals 0 to infinity, 1 over 3 to the n, plus sum n equals 0 to infinity, 2 to the n over 3 to the n, and I can work with each sum individually. So I'm going to call them 1 and 2, and I'll work with each of them separately. So let's start with sum 1. So I have sum n equals 0 to infinity, 1 over 3 to the n, and again I'm not in the same form as what I have in the formula, but that's okay. I'll just write out the first several terms and try to identify a and r if the series is geometric. So for n equals 0, I get 1 over 3 to the 0 is 1, and then I get plus 1 over 3, and then I get plus 1 over 9, plus 1 over 27, etc. So we see that this first series is in fact geometric, with first term a is equal to 1, common ratio r is equal to 1/3. The absolute value of a third is less than 1, so our series converges, and using our formula, the sum of the first series is 1 over 1 minus a third, so I get 1 over 2/3, which gives me 3/2. So the sum of our first series is equal to 3/2. Now let's work on the second one. So for the second one, we have sum n equals 0 to infinity, 2 to the n over 3 to the n. When n is 0, we just get 1. When n is 2, we get 1, we get 2/3. When n is 2, we get 4/9. When n is 3, we get 8 over 27. And we see again, this second one is also a geometric series. The first term is again a is equal to 1. Common ratio this time is 2/3. The absolute value of 2/3 is less than 1, which tells me that my series converges. And using my formula, so we get a, which is 1 over 1 minus r, so 1 over 1 minus 2/3, which gives us 1 over 1/3, which gives us 3. So the sum of the first series is 3/2, the sum of the second series is 3. That means the overall series also converges, and the overall series, the value of the sum is equal to 3/2 plus 3. 3 is 6 over 2, so this gives us an overall sum of 9/2, or 4.5. So the key to this one was breaking it up and looking at the series as two individual sums. We were able to see that each of these was geometric, so we could use our formula individually and then go back and say that the overall series converges. Next example, we have sum n equals 0 to infinity, 2 to the 2n, 3 to the 1 minus n. Again, not in the form of what we had in our formula, but that's okay. Let's just start writing out terms and see if we can identify whether or not this series is geometric. When n is 0, I get 2 to the 0, which is 1 times 3 to the 1, so 3 for our first term. When n is 1, I get 2 to the 2 times 3 to the 0. When n is 2, I get 2 to the 4 times 3 to the minus 1. When n is 3, I'm getting 2 to the 6 times 3 to the minus 2. When n, I'll do one more, is 4, we're getting 2 to the 8 times 3 to the minus 3. And we can see now again, I do have a common ratio between terms. So this is, again, a geometric series with, so the first term here is a is equal to 3. The common ratio, so notice that at each stage I'm multiplying by 2 squared times 3 to the minus 1, or 2 squared over 3. So at each stage I'm increasing the power of 2 by a factor of 2 and decreasing the power of 3, or increasing a 3 on the denominator. So make sure you understand that step. Write out the first line in more detail if you need to. So notice, for example, this is 2 to the 4 over 3. This term is 2 to the 6 over 3 squared. This term is 2 to the 8 over 3 cubed. So make sure you see why the common ratio is 2 squared over 3, or 4 over 3. So our common ratio is 4 over 3. Notice that the absolute value of 4/3 is greater than 1, which tells us that this geometric series diverges. So the term that as we add up more and more terms of this geometric series, the sums would just be getting larger and larger and larger. Now let's make sure we can identify this in sigma notation, the way that it's given in our formula. So remember, our formula was sum n equals 1 to infinity, ar to the n minus 1, so a is 3. R we said was 4/3 to the n minus 1. Let's make sure that this really is the same series as what we have above. So when n is 1, we just get 3. When n is 2, we get 3 times 4/3, so which just gives us 4, which does match up with what we had before, since 3 to the 0 is 1. When n is 3, we now get 3 times 4 squared over 3 squared. So let's see if that term matches up. So our next term was 2 to the 4 over 3. Is that what we have here? So 4 squared, that is 16, which is 2 to the 4. 3 over 3 squared just gives us a 3 in the denominator, which is the same thing. I'll just do one more. So our next term would be 3 times, when n is 4 now, we have 4 cubed over 3 cubed. 4 cubed, so again, let's see if that's 2 to the 6 over 3 squared. 3 over 3 cubed is a 3 squared in the denominator, so that's correct. 4 cubed, remember 4 is just 2 squared, so 2 squared all cubed, which does give us 2 to the 6 over 3 squared. So this is the same expression as what we had, as what was given, but again, what I want to emphasize is that I think it's much easier if you just write out the first several terms, identify the a and the r, instead of trying to go through the sigma notation. Again, either way is totally fine. I just think it's slightly easier if we use the writing out method. So just to conclude, geometric series, the key, identify your first term a, identify r, your common ratio. You can either do that by writing out the terms, which I think is the slightly easier method, or you can get it in the proper sigma notation and identify a and r from there.